Hello and welcome to my CST beginner guide. In this video, I'm going to show you how to take a transmission line, a microstrip transmission line, and terminate one of the ends. I'm also going to show you how to understand and interpret data when there's a mismatch load, such as a 100 ohm load up to 150. The first thing you want to do is design your 50 ohm microstrip line. This is a 50 ohm line created on magnesium oxide, which has a relative permittivity of 9.7. Its thickness is 0.5. And I've set the PEC as the conducting material to speed up the simulation time. Okay, so the first thing we want to do is we want to simulate our line. Now we have two options. We can terminate this in the schematic tool, or we can keep everything in 3D. In this video, I'm going to keep it all in the 3D environment, but in a later video, I'm going to explore the schematic view. The first thing we want to do is we want to actually get rid of one of the ports. So I'm going to delete port 2. Click on navigation tree, right click port 2, delete. Do you really want to delete this? Yes. Delete results. Okay. I'm going to control click to go over to our other port here. And what we're going to do is we're going to set a lumped element between the face of the microstrip line and then the face of this ground plane. Okay, to do so, what we're going to do is we're going to select two edges. We're going to pick edge and we're going to pick the top of this line here. And then we're going to do the exact same. We can click E as a shortcut on our keyboard. And I'm just going to select the ground plane over on my left-hand navigation tree to make it a bit easier. And I'm going to select the top line of the ground plane. Perfect. Now we have our 2 points, or our 2 edges. I'm going to navigate over to Simulation, Lumped Elements. Here, I'm going to terminate it to 50 ohms. Click OK. Click on components to see everything. And there we go. Now we have a lumped element between this length of the microstrip line and between the length of ground. Okay. Let's reset our view. And let's double check our boundary conditions. So with the following boundary conditions set in the previous video, I'm quite happy by having a ground on either side of the substrate, not touching the transmission line, and I want a ground also on the bottom, and I'm happy with open add space on the sides where the ports are and the lumped element. Click OK. Okay, I'm going to run the simulation and I'm going to select normalize to 50 ohms, and I'll be back when this is completed. Okay, the simulation's complete. It took about 1 minute of time. Now let's head over to our 1D results. So, noting that we only have one port, so there's only going to be one result. That's our S11. So, let's now change our S11 so that we can see the top of the graph actually at 0. So here in our y-axis, I'm going to force that to be 0. And now we have a similar graph as before. So we can see very good reflections. There's minimum reflections. So everything is matched quite well. But to double check everything, let's go back to the results. To double check everything, I'm going to click on this tool here, Smith chart. Now, as we can see, the Smith chart with a 50 ohm load, yeah, it's good. It's matched quite well. We can see maybe if the load was 49 or a little bit more than 50 ohms, we'd see a more better or correct match. Ideally, we don't want any circle, we want it as small as possible. And if we zoom all the way out, we can see it's quite a small circle here. So it's matched quite well. Okay, so these are the results of a 50 ohm line. Well, now what happens if we change this to 100 ohms? Now we should know from learnings about the Smith chart, we should see the same circle here, but actually we should see expanded all the way out from this point at 0.5 and then all the way out to 2. We should see quite a large circle. So let's have a go testing that. What we're going to do is go back to our 3D environment. We're going to head over to our lumped element, folder 1, double click on lumped element. This is the history tree, so if you need to then change anything, for example, you need to change the material or change the size of an object, you can double click on it, for example, double clicking on a component. But in this case, I'm double clicking on element 1, I'm double clicking on define lumped element, and here I'm going to change the resistive load to 100. I'm going to click OK, I'm going to delete the previous results, I'm going to close this window, and I'm going to do the exact same simulation normalized to 50. Okay, the simulation's done. Let's check our S11. Okay, perfect. We can see, well, let's change the max value here to 0 again. And we can bring it back to maybe -30 like it was in the previous case. As we can see, this line, this performance, is much worse. So we're getting a lot of reflections. Before, it was down between 20 and -25, so little small amount of reflections, but here at 10 we're starting to see maybe 10% or more than 10% of the power being reflected back to the source. Now to view this, it's best to open the Smith chart, and we can see it's perfectly lined up with 2 and hopefully with 0.5. Okay, so we can see our Smith chart represents this perfectly. Okay, now I'm going to go over another tool which is called parameter sweep. So instead of setting a finite value for the lumped element, we're actually going to make a variable called resistor, RES, and we're going to set it to be 50. Enter. I'm going to double click on the element and define lumped element through the history tree, and I'm going to replace the 100 with RES. I'm going to click OK, then OK. Close this back down. Now I'm going to set up the simulation solver. On the side here, there's a parameter suite, par sweep. Click on this box. We're going to go new sequence, new parameter. Name of the parameter, RES. Now we have a choice of linear sweep. For example, we can set from 50 to 100 with maybe 3 points. And then we can click OK, and then here are our points, 50, 75, 100. That'll be quite a nice simulation. Or we can try, for example, let's go edit, change it to arbitrary points. So I know that 50 was nearly matched, so I'm going to go 48, 49, 50, 51, 52, and I'm going to see 100 again, and maybe I'll try 200, see what happens when the load's even more mismatched. I can click OK. I can click check if there's a moving geometry. For example, you could be changing lengths, or you could have a stub you're changing lengths or thickness. And the checking tool allows you to see how the geometries change on the substrate. Currently, the resistor value won't do any geometry changes, so we don't really need to check that. We can just click start. Okay, clicking start. So this should take, let's say if we have 7 initial sweeps, 7 times the 1 minute it takes to do one. For all this to simulate. So I'll be back when this finishes. Okay, the simulation is done now. Now, I encountered one error where if you create a lumped element port, on the first time when creating it, that is when you need to put in your variable name. If you set it to be an integer value of 50, and then I applied the variable name post creating the item via editing the history tree, it seemed to have not have worked, so I resimulated and replaced a lumped element and simulated for the exact same conditions as before. Okay, let's check out our results. So let's go to the first run. We find when the load is now 48, we're seeing reflections down to -50, some very good match conditions, and let's check that on the Smith chart. We see actually at 49 ohms, we have a better match condition. 48, sorry. Let's jump to 48, and we see the Smith chart slowly expanding. And here's our 50, 51, 52. Okay, and now we can see our mismatch condition of 100 ohms and another mismatch condition of 200 ohms. Okay, perfect. So this is the simulation results from a mismatched load. In later videos, we'll then discuss how we can then simulate a impedance matching circuit. Okay, thank you.